Good afternoon, everybody. Welcome to the third lecture of the first module on space-time codes and MIMO. In the first class or first lecture, we have introduced various topics. Second lecture, we have basically shown how MIMO will actually increase the capacity. What is the main benefit of MIMO? Okay, we saw that it leads to an increase in average capacity, and we introduced various concepts of outage, etc. And then we linked it and showed that in a fading channel, the outage is the main contributor to errors, and the outage is due to fading when the received power is below a certain threshold. Okay. In today's talk, there are two agenda items. Okay. So we'll basically be introducing space-time codes here. And how do we do that? We will actually derive the BR for MIMO communication systems. I will lead you through the entire process, right from the CISO AWG channel to MIMO fading channels, and show you how the actual design rules come. And then I will introduce one example of orthogonal space-time block codes. Okay. And in doing that, I will also link back to the diversity encoding grain criteria that we stated in the first class. So with that, we will actually close both the links that were open in the first lecture. I close the first link, relation between epsilon of the erasure channel to 1 by gamma the SNR in the fading channel, last class. Today's class I will close the second open link. Okay. So let us go forward. So now from the last lecture we have seen that there are two different cases. There is the fading channel ergodic, that it is changing every channel instance. It's quite fading fast enough, so that gives you an average throughput that is possible on a channel. Okay. For such a case, any channel, any code that is designed for AWCN actually works. Okay. So there is no issue. This reason, the reason why this happens is any code that is designed for AWGN channel, you can just map it to the real domain using modulation, and that will work over an ergodic channel. Because as we have seen before, it is the dmin that dominates, and because we know codes that have large enough dmin, so we will achieve all the degrees of real time required and all the diversity that is required, so there is not much that is needed to be done. However, the concept of outage is very important. Codes designed for taking care of outage that comes because of slow fading channel. Okay. So once the signal power is very small, the possibility that you are going to get a good signal is going to be very far off. So what do you do in such a case? Okay. In such a case, to compensate for randomness, we have already seen the idea is to introduce diversity, that you transmit the signal on multiple channels. Okay. So this is a bit of randomness. Coding gives you, so the coding for non-ergodic channels will give a mix of both. The randomness that is being incorporated by dividing the channel over multiple channels, and determinism coming from traditional coding. So both of them are required here. So in this class, because for the fast fading channels we have already addressed that whatever is the coding that has been defined for AWGN can be directly applied for channels, ergodic channels, fast fading channels. So our emphasis now is for channels that are not ergodic. In this first lecture, remember that we introduced a repetition code. Okay. And we actually introduced very general repetition code where the repetition was 3. Remember that I gave an example. Then I showed that it has a diversity order of 3. Okay. so on and so forth. Now, what will happen in a memo case? So, let us start with an example. So, you have a simple AWGN, I would say a simple channel here, where there is one transmitter, okay, but there are two receivers. So, signal from the transmitter, okay, this is RX1 and this is RX2. There are two receivers. Yeah. So even if the markings are not clear enough, just see that this is one transmitter, two receivers. The received signal as the first receiver is basically given by this equation, where H1 is the fading coefficient from transmitter 1 to receiver 1. Eta 1 is the additive void Gaussian noise, similar case for eta 2. Now you see, because there is one transmitter, there is only one symbol that is transmitted, and you want to recover that. What is it that you can do? You have the same signal received at two antennas. Same information received from two antennas. So one simple thing that you can think of is basically multiply each what signal that you have received with a weight and then try to make an estimate on it. Okay, so I multiplied with W1 for is the weight for the first receiver, W2 is the weight for the second receiver, and then I have collected terms. So you see, this is the combined term for the signal X that we want to recover, and it is multiplied by W1 H1. So H1 is the channel from transmitter 1 to receiver 1. W1 is the weight at the receiver 1. Similarly, at the second, W2 is the weight at the receiver 2 and H2 is the second channel. Okay. So now we can write in the terms of SNR. What is the signal to noise ratio? Okay. So the signal to noise ratio is the expected value of this. This is a deterministic, the first term, the underlying term is deterministic. Okay. So square of that. X is a random variable, so we have E of X square that gives you the average. E of X square is nothing but the power, average transmit power. And the expectation of this gives you the noise variance. We have assumed eta 1 and eta 2 are variance 1. So in this case, what you have is the instantaneous SNR given by this formula. Okay. Now, in this case, if we take W1 as conjugate of H1 and W2 as conjugate of H2, what you can see is you have a very nice term, the signal to noise ratio after combination is the signal to noise. See that H1 square plus H2 square, expected value of H1 square, this you can replace as the signal to noise ratio gamma of a single channel. So I will, to make the difference, I am putting a bar on that. Okay. So H1 square multiplied by gamma 1 is the SNR if only only one receiver was there. H2 square plus multiplied by gamma bar is the SNR at the if only the second receiver is there. And now you see here, by choosing W1 and W2 appropriately, we have been able to actually combine the SNRs of the two signals. Okay. Now I can claim here that the diversity is 2. Any ideas why? It is very straightforward. You see the instantaneous SNR gamma, it depends on H1 square plus H2 square. So the SNR will only be bad if both H1 square and H2 square are bad. So it has actually taken care. This method of combining has taken care that the received SNR will be bad only when the case when both the channels are bad. Okay, and we know already from our analysis of outage last class that the probability that both the channels are bad is square power. Okay, so it is 1 by gamma power 2. Okay, so we are already achieving a diversity order of 2. So one simple 1 cross 2 SIMO channel, see that we are getting a gain, diversity gain of order 2. So this is one example. Let us take another example. It is not, see for the, remember last class I have given you exercise that from an outage perspective, I asked you to show that the SIMO is equivalent to a meso channel, right? I hope you have done the exercise. But from a coding perspective, they are not same. And that's what I wanted to see from you. So now I have turned the problem around. You have a meso channel, that is you have two transmitters. Let me draw it a bit clearly. Transmitter 1, transmitter 2, and you have a single receiver. Okay, so what you transmit from here is x1, and what you transmit from the second transmitter is x2. Okay, both of them, they are combined by the space, by the antenna at the receiver. Both of them are combined. So what you get at the single receiver antenna is basically Y1. It is a combination of H1, H2. Okay. Previously we had transmitted only X1 at the transmitter and only X2 at the transmitter. But now in this case, we need to do something. And to do something, what I have done is we have multiplied or we have transmitted not just X1, we have transmitted W1 X1. So we have done some pre-coding at the transmitter. And similarly W2 is the weight that we are applying at the transmitter. So these are what are called as the pre-weights or the transmitter weights. Now again, going as in the previous case, the instantaneous SNR at the receiver is now given by W1H1 plus W2H2 square plus E of X square, where X is now a vector X1, X2. And we are assuming that expected value of X1 is same as expected value of X2, so it comes out of as E of X square. Okay? Excuse me for that. And we have assumed that the AWG and noise has variance 1. So this E of X square is also can be written as gamma bar is the SNR at the receiver. Average SNR at the single receiver for a CISO channel. Now suppose at the transmitter you know the channel H1 and H2. That is the effect of the channel from transmitter 1 to receiver 1 and transmitter 2 to receiver 2 is known a priori. It is known beforehand. So in this case we can do a very nice trick. So we can choose weight W1 as conjugate of H1 and weight W2 as conjugate of H2. And in this case you see we have again got back the SNR that we have got for 1 cross 2 channel. In fact there is an addition here. So you actually need to if you choose as conjugate of HI, what you will get is square of. Okay, the square term is missing. Okay, but you need to do some normalization here, so that the total power transmitted is unity. So in that case, this square term will go down. So what you actually multiply is by conjugate of HI by summation of HI square. Okay, so that is what WI is chosen as. I'll write it down. What it actually should be is HI, yeah, the precision is not good, by, this is I. Summation, yeah, just take it as HI. I am not able to write the dot here properly. Okay, so this is the weight you have chosen. HI conjugate by summation of HI square. In this case, the square term will not be there here. And you can again see that you have got diversity out there too, because you have been able to combine the SNR of two channels separately. But the important catch is this: to have Wi of this form, to have it as a function of the channel has to be known at the transmitter a priori. It has to be known beforehand. So that may not be always possible. It may be costly to do that. This is because typically you will have to have a dedicated channel to send back the channel information to the transmitter. So it is not always practical. What do you do in such a case? Okay, can something be done? So the previous 1 cross 2 SIMO channel that we described in the previous channel, it is called as maximal ratio combining. If you do the maths, if you write the SNR for a general WI and then try to find out W1 and W2 so that you want to maximize SNR, you will see that what we have done in this, okay, in the 1 cross 2 SIMO example, by choosing W1 Wi as conjugate of Hi, we have done one thing. What? We have maximized the SNR. This is the maximum SNR that is possible. This W1 and this W2 will give you the maximum SNR. The SNR cannot be greater than this. So this is what is called as the maximal ratio combining, MRC. Okay. This is what is called as the MRC, maximal ratio combining. Similarly, for the 2 cross 1 MISO that we have discussed just now, we are able to get a diversity order of 2 provided the channel is known at the transmitter and these weights or the one that I have written by weighted HI is HI conjugate divided by weight of the divided by the weight of that sum of squares is what is known as the maximal ratio transmission. That weight is the optimal weight. Okay, that WI is the optimal WI that will maximize the SNR. So this is what is called as a maximal ratio transmission. How can you solve that? You take this equation, differentiate it with respect to W1, okay, under the constraint that weight of W1 is fixed. If you keep increasing weight of W1, then the sum of weights has to have a fixed value, that is W1 square plus W2 square has to be less than a certain threshold and that is taken as 1. That is called as a unity constraint. So under that constraint, differentiating with respect to W1 and W2 will give you these optimal thresholds. Okay. But suppose this is not known at the transmitter. What do you do? Then if you don't know H1, H2, it will be this is some linear combination of H1 and H2. Remember, H1 is a complex Gaussian random variable. Similarly, H2 is a complex Gaussian random variable. Summation of linear sum of two Gaussian random variables is a Gaussian random variable. Okay. So what you get is by taking, if W1 and W2 are not a function of H1 and H2, then you will get a single order term. That is, the diversity order will be of only 1. So can we do something in this case? The answer is yes. Okay, and this is what was proposed by Almaty, and that actually made the space-time equals very, very popular. So you have what you call these are the two antennas, X1 and X is what is transmitted. Okay, it is transmitted over 2 time intervals. X1 and X2 are two symbols that are transmitted, but in the second time interval, okay, a function of X1, X2 is transmitted. Here it is minus X2 star and X1 star. This row is on transmitted on antenna 1. So this direction is basically time. This is what is transmitted in time duration 1. This is what is transmitted in time duration 2. Along the columns is the space duration S. So this is transmit antenna 1, this is transmit antenna 2. Okay? So this is a space-time code. You have taken two symbols and a combination in a different combination is transmitted in space and time. So this is a space-time code. Two time periods are required to transmit this code, and the rate of this code is NT times rate of the code, basic code, and log Q times the constellation. Okay? Number of transit antennas is 2, rate of the code. You see that the basic code is actually replicating x1 to y. So you can see that the basic code is actually a rate half code. If suppose only x1 is transmitted, then the rate would have been half. So the underlying code is of the form that the first symbol is repeated and transmitted after conjugation. Similarly, the second symbol is conjugated and negated and transmitted. So the rate of the underlying code is taken as half, and the effective rate of this overall channel is basically equal to Q, that is of the Q curve, Q of the Q curve. Okay, that means by doing this replication, while we are repeating it, because of the additional dimension in space, we are able to say that there is no penalty as compared to the seesaw channel. The rate of the seesaw channel is same as the rate of the MIMO channel here using this arrow mounted code. Now, what would be the output in this case? It is very simple. Y will be the output, H is the transmit matrix, X is this vector now, okay, and eta. Suppose you have one receiver only. So Y is 1 cross 2 and eta is also 1 cross 2. These are complex Gaussian random variables because eta is a complex Gaussian random variable. Now suppose H is a 2 cross 1 channel. So I am assuming, as in the previous case, 2 transmitters and 1 receiver. Okay, the channel model is clear. H is H1, H2. H1 is from transmitter 1 to receiver 1, H2 is from transmitter 2 to receiver 1. There is only one receiver. So you have two outputs. Why do you have two outputs? Because we have used two time durations. Remember this. This is the present y is equal to hx plus eta notation is different from the notation that we have of MIMO we have used before. Because there it was only for one channel duration. Here this y is for two channel durations. Because we have x is such that we have used two time durations to transmit it. Okay? Any questions there? Okay. Now we can do the maths. Multiply H1, the vector capital H with the matrix X, and this is what you will get. So you see a linear combination of X1 and X2 is transmitted. So both Y1 and Y2 have information about X1 and X2. Okay. Now can we do something? Can we simplify this? Answer is yes. So here we have just taken conjugate of Y2. So here we have removed the conjugate and the conjugate has now gone to the channel coefficients and the noise. You see Y2, eta 2 conjugate, H2 conjugate, H1 conjugate. Now we write it again in a matrix form. So let Y1, Y2 star be written as the vector italics Y. We take out H1, X2 and form the equivalent channel matrix H italics, and eta 1, eta 2 star we represent as theta, the equivalent noise. See, because eta 1 and eta 2 are independent, eta 1, eta 2 star will also be independent. This is a very nice combination. We started with transmitting a replica of x1 and x2. What we have landed it, we have put this repeated transmission of x1 and x2 as actually put a structure on the receive channel. You see that? Just multiply and see that this is same as this. This is, see, x1, h2, x2. So this is same, eta 1 same. So this is the first equation. Second equation, h2 star x1, this is this one, and minus h1 star x2, this is this one. Okay, so you see that it's the exactly same equation, but it has changed the entire things, put the entire thing into different form. Now I can take out x1 and x2. So if I take out x and x2, this is a very different matrix from what I would have seen. The channel matrix h1 and h2, but because of coding, I see the channel as a matrix form. It is no longer a vector. It has now become a matrix and it has a structure. Let us see what that structure is. Yeah, we'll come back to that here. This equivalent, this H italics is called as a equivalent channel matrix, and it has a nice property. It is an orthogonal matrix. So what's an orthogonal matrix? A square matrix O is said to be orthogonal if and only if O conjugate O is equal to O conjugate is equal to an identity matrix multiplied by a scalar. So now just do the maths. Do H Hermitian, that is calculate this and tell me what it is. I want you to evaluate. Yeah, tell me what this is equal to. It's simple matrix multiplication. Do it fast, let me see what it is. Verify that it is on. Tell me verify that it is orthogonal and tell me what is the A for this case. What is the scalar? Yeah, anybody? I am waiting for the answer. Yeah, it is sum of squares of the fading coefficients. That's good. Excellent. One answer. Okay. So you see, this simple replication has put a structure. Now, how does that help it? Now also see that the transmit matrix, the space-time code X that we defined last class, that also is an orthogonal matrix. So take that as an exercise for today's class. Okay. Last class I have asked for 3. This is the first exercise for today's class. See that X is also an orthogonal matrix. Now I have explained to you that this is a space-time code because there is a coding in both space and time. Right? And it also has a property that it is orthogonal, so such codes are called as orthogonal space-time codes. It is a block code because you are transmitting only a block. That is, you are transmitting only 2 symbols. If you transmit a block of n symbols, it's still a block code. If you are doing continuous coding, like in convolution codes, it is no longer a block code. Okay? Or a turbo code. It is no longer a block code. Okay? So this is an example of orthogonal space-time block codes. You get the point? OSTBCs, because of this orthogonality, have a very nice property. So we already know that H is a orthogonal matrix. So let me multiply conjugate of H italics to the processed Y matrix, that is Y italics that we defined in last slide. So multiplying that, this is what we get. First line, we know H conjugate H is basically identity matrix with weights H1 square and H2 square. That is, this is a scalar. That's the exercise I wanted you to do. I got one answer from TC. That's good. I hope others have also done it. Now, this is your noise term. Eta 1 and eta 2, because they are independent, Now you have a new noise term, H conjugate theta. This is again independent. You can see this as follows. So our equivalent noise now, theta bar, is basically equal to H italics conjugate theta. And where theta is basically equivalent to theta 1, theta 2 conjugate. These are two AWGN noise, and so we know expected. They are independent, so we know this is equivalent to sigma square I. Where sigma square is the variance of noise, and I am assuming it to be equal to 1. Okay. Now let me find what is the covariance of theta bar, the one multiplied by H conjugate. I am rounding off this term. Okay. So do the maths here. So this would be expected value of I am just substituting, that's all. This would be theta dagger and this would be your H matrix. Okay. Now given H, given the channel at the receiver, both of these are known, so this essentially becomes expected value of, you can take the expectation inside for, because this is the random term, right? This is the random variable, this is known, both of these are known. Okay, so taking it inside, what you get is H conjugate, expected value of theta conjugate now this we know is a scaled identity matrix I2, right, the inner term. So substituting and again doing it and again doing the multiplication, this is what you get. What that tells you is multiplying by the H italics matrix keeps the two equivalent noise terms eta 1 bar and eta 2 bar. Okay, these are the two equivalent noise terms. They are independent, but they are scaled by a variance that is equivalent to H1 square, H2 square. Okay, see that. So this covariance matrix says that the equivalent noise given by the vector theta bar, the components eta 1 bar, eta 2 bar, they are still independent, but their variance has now been squared by a value that is given by the scalar. Okay, so the noises are still independent. That's good. So using this, going back and applying here, so these two are independent, and what is happening here? X, capital X is basically X1 and X2. Remember in the previous slide. See this, capital X, it consists of X1 and X2. Okay. So what you have by multiplying H conjugate with Y italics, okay, the first equation, because it is I2, H1 H2 square is a scalar, okay, I2 is a diagonal matrix. So the first equation, it depends only on X1, the second equation depends on only X2, and the noise terms, they are independent. So this we can now decode X1 and X2 separately. Okay. For clarity sake, let me write as Z1 is equal to this value. Z is a vector that is equal to H italics conjugate multiplied by Y. Okay. So now it is simple exercise to see that the first element of this vector. So your Z1 is basically H1 square plus H2 square X1 plus eta 1 bar. Okay. Similarly, Z2 is basically similar terms X2 plus eta 2 bar. Okay. So now you see Z1 and Z2 only depend on X1 and X2, and eta 1 and eta 2 are independent. So these two equations are independent and you can decode them separately. Okay, and because of this H1 square H2 square term, you see that by the same argument we had for MRC and MRT, 1 cross 2 and 2 cross 1, these have a signal to noise ratio equivalent to, so what is the signal, right? Let me write instantaneous signal to noise ratio of eta 1. What is that equivalent to? Square of the first term. Okay. So that will be H1 square plus H2 square whole square, expected value of E of X1 square. Okay. Divided by noise variance. Remember, what is the variance of eta 1? We have already derived that. It is H1 square plus H2 square. We have derived. So the square term above here cancels with this term, and what you have is X1 square H2 square E of X1. This term is basically equivalent to the average signal to noise ratio on a signal to noise, and you can see from the effective SNR for the first channel that it will fade or it will have a bad SNR only if both H1 and H2 are small. That is, we have achieved a diversity order of 2 by gamma square. So we have already achieved a diversity order of 2. Okay. So even if you don't know the channel at the transmitter, there is no problem. What you need to do is space-time coding. Okay. In doing so, we have also done an additional thing, and that's what I want to introduce now. Okay. We have solved one important problem of space-time codes. So by these three examples, I have introduced the concept of space-time coding, and I have also introduced the concept of block coding. Now I am introducing a third concept. Just be with me. Okay, I am going to share the screen with you. What you see is an optimum receiver for AWGN, basics that you have done in digital communication by ProArchis chapter 5. So you see that you receive signal, you are multiplying by the capital N basis functions, and there you make a decision on what you get vector output from all of this. Right? Now, what is the optimum detector for a vector AWM channel? There the case was what we derived the theory in ProArchis chapter 5 on a general case, but then we applied it for a CISO channel, for the complex CISO channel. What happens when the channel is a MIMO channel? Okay, so there suppose you have transmitted a vector X, complex vector X, you are receiving complex vector Y, which is the summation of transmitted symbol X, complex transmitted vector X, and the complex noise vector eta. There is one important point here. What is that? The probability in the CISO case, X would take, say, take values from BPSK or QPSK, so the number of symbols possible would be capital M. if it is say 4 QAM, okay, if it is 4 QAM, then the number of values x would take would be 4. But now there are NT complex numbers, okay, each number takes value from a m dimensional constellation. So number of possible candidate vectors is basically m power, right, m power nt, because each variable will take a value from a m dimensional or a m array constellation, say m QAM or m PSK or m amplitude modulation, whatever, okay. But because each one is taking a value from an M-array constellation, the total number of possible candidate vectors xm that are transmitted is m power nt, okay. So it is exponentially 90. What would be the maximum likelihood detector? See, I am just exactly following your Proarchis chapter 5 derivation. So what is it? Your map rule, you maximize the probability of receiving xm when y was transmitted, where m takes values 1 to m power nt. Okay, this m is because I just lifted the equations from the textbook, that is Proarchis. So excuse me for that, this is not just m, it is m power nt. All these are m power nt. Okay, xm takes 1 to m power nt different values. Applying your base theorem, you can rearrange this, right? Now py, it is common to all of them, so you can drop it. You will get this equation. If each of them xm, probability of xm is equally likely, you can drop that and you get what is called as a maximum likelihood detection rule, and this py given xm is called as the likelihood function. And a likelihood rule is this: you maximize p of probability of receiving y given xm was transmitted for all possible m, small m's, and small m takes values from 1 to power. That is important, m power nt, just put that in mind. So now, assuming each noise vector has, each component of the noise vector eta, that is eta 1, eta 2, eta 1 is a complex Gaussian with variance sigma square, you can write the density function of each of eta k as follows, right? And this is all standard stuff from your textbook, but important point is your y is, here it says nr, but is it nr? Dimensions will not match. Here it has to be nt, it has to be same dimension. So under the constraint that nr is equal to nt, this entire equation holds. Okay, right? Under this PDF, so this is the conditional PDF, or this is the noise PDF for each eta k. So they are total nr equal to nt total such values. So probability y given xm is basically, because each of eta k is independent, you can write it as product of this and just substitution there, and this is what you get, the third equation here, right? And product of exponents, the product term, this can be taken inside, so it becomes a summation, k equal to y nr. And because this is a constant term, it can be removed. Exponential is in the range of interest, that is positive values of this, it is going to be a 1-to-1 function, so I can take a log function here, and this is what I get. Maximizing over py given xm over all possible m is equivalent to minimizing over m over all possible m, the summation of yk minus xmk. And last class I had defined the Frobenius norm, so it is equivalent to reducing, finding the a vector xm that has the shortest distance from the received vector y. Okay, so it's just exactly telling the concept that we have developed for digital communication, except that now the dimensions have increased. There it was a one single complex dimension. Now They are NR equal to NT complex dimensions. Okay. So second slide, the correct, just make a remark or first and second slide, just make a note that these equations y equal to x plus eta holds only in the case when NR equal to NT. And we have a very nice fallback to what we have learned from digital communications, that the optimal rule, even though it is now a vector, is same. You just need to find a vector xm that has the smallest distance from the received vector y. Fine? Let's go ahead. Now what happens when an AWGN channel, but it is scaled by a matrix H, right? So now you have the case y is equal to Hx plus eta, and now your matrix H has dimensions nr cross nt and y has dimensions nr cross 1, okay, and x has dimensions nt cross 1, okay. Same equations will hold, okay, but the constraint nr nt is not required, so this is as it is, this equation, okay. And then what you have is slightly different now. The probability of, previously we maximized the probability of y given xm, the likelihood function. Now we are maximizing the probability of y given hxm, okay, given hxm. So hxm can be actually thought as the vector as seen by the receiver. What was transmitted was x at the transmitter, but what is received at the without noise at the receiver is hx. Okay, so this H matrix is actually moving NT-dimensional transmit vector to an NR-dimensional vector in the received space. Okay. So it's just see that in your mind, it's a graphical interpretation. Okay, and with that everything else will hold, and your ML role is again basically now distance between the received vector y and the transmit vector as seen from the receiver's perspective, that is hxm. Okay. But the important point is this. Now, how many times you need to calculate this rule? Suppose y is one dimensional. So, how many times you would calculate this vector? M times. Suppose nt is equal to 2. How many times this vector has to be calculated? Because there are going to be m square number of xm's. X possible candidate transmit vectors. Okay, so the total number of symbols that total number of distances that you are going to calculate is going to be m square. If nt is equal to 4, it is going to be m power 4. So if you are not realizing the significance, just take BPSK. Nt is equal to 1, you need to calculate only two distances. Now take the case nt is equal to 2. How many distances you need to calculate? Square. Okay, 2 square, that would be 4. Now take nt is equal to 8. How many distances you need to calculate? 2 power 8. How much is that? 256, right? So you need to calculate 256 for a simple nt is equal to 8 matrix. So it is increasing exponentially. The complexity is increasing exponentially. So that is one of the major problems of space-time course. Decoding complexity is exponential in number of transmit antennas. We need to come up with a simple solution. And before giving the problem itself, we have seen that if you use orthogonal space-time codes, okay, then in this case, if you use orthogonal space-time codes, then the decoding complexity has been reduced. What is the decoding complexity for the Almaty cost we have been discussing? Yes, we see it. Excellent. Yes, anybody? What is the complexity for the Almaty code after decoupling? How many times do you need to calculate the metric for BPSK? In this case, there is one answer. See, the answer is straightforward because you are decoupling x1 and x2. Z1 depends only on x1 and Z2 depends only on x2. So when you calculate distance for x1, you only need to calculate two matrices for deciding x1 and two matrices or two distances for deciding for x2. So total is 2 times m. Okay. So where m is your constellation size. So the complexity here for the Almaty case is 2m. For normal space-time code, the complexity is m. For a nt is equal to 2, the complexity is m square, right? For Almaty code, it is 2m. So you see, instead of exponential, the complexity has become linear, and that is a huge advantage. And that's why Almaty code is now a de facto standard. All wireless standards have Almaty code as the one of the transmit schemes. Okay. What happens? Can we do something more? This is only for NT equal to 2. What happens if we have more number of antennas? So there is a problem. So here are two examples. For NT equal to 3 and NT equal to 4, you see rate of the underlying code is now 3 by 4. You have three symbols, they have been spread over 4 time duration. So that's why the rate of the underlying code is 3 by 4. Okay. So these are three transmit antennas. Remember the notation I introduced. Along the column it is the antennas. So this is antenna 1, antenna 2, antenna 3. Along the row. Okay, this is the time direction. So this is time instant 1, time instant 2, time instant 3, time instant 4. Okay, so this is a orthogonal space-time block code for 3 transmit antennas. Verify that these are orthogonals. Okay, same case with here. So what is the problem here? By increasing the number of antennas, you have paid a penalty. If it were a rate 1 code, you would have transmitted 4 symbols, but you are now transmitting only 3 symbols. Okay. So this is a major drawback of space-time, orthogonal space-time block codes. It allows to decode simply, so decoding complexity is linear, it is no longer exponential, but you are paying in rate. You cannot have good things both sides, here and there. Okay. Can we do something there? The answer is yes. So in this case, you need to now generalize space-time block codes to a more general class that is called as the linear space-time block code. So I'll just define what is a linear space-time block code. A linear space-time block code X, okay, is defined as a linear combination of the transmit symbol that you want to transmit, xi, multiplied by weight matrices called the distribution matrices that distribute the symbol xi in space and time. Suppose you are transmitting L such symbols. Okay. So for the Almaty code, you have x is equal to x1, x2 minus x1 star, x2 star, or just check it, I think it's plus or minus 1. What is it? Yeah, this is minus x2 star and this is x1 star. Okay. Now what is A1 in this case? A1 is basically equivalent to 1, 1, 0, 0. Okay. Similarly, A2 would be equal to, yes, now you have a problem. In fact, even A1 cannot be written as 101. What you need to do is, you need to define xi star bi. Okay. So this is not with that notation change. Okay. So A2 becomes 0, 1, 0, 0. Okay. What is B1? It would be 0, minus 1. Remember that. Okay. So codes of this form in the square, okay, these are called as the linear space-time block codes. Okay. So you see, the orthogonal space-time block codes are a special case of linear space-time block codes. Okay. So orthogonal space-time block codes we have seen for nt greater than 2, they suffer from very small rate. So can we do something? The answer is yes, you need to, but you pay somewhere else. So you slightly increase the complexity, but you still get the rate. Okay, you increase the rate and you decrease the complexity. That's how it works. So with various trade-offs of rate, what is decoding gives you the entire gamut of space-time block codes. Okay. So now we now need to do something much more formally. We have come up with a very general definition of a linear space-time block code. Now we want to know how to design such a space-time block code. Okay. To do that, I will now give you some formal derivations of how things are actually happening so that you become a bit more comfortable. Okay. I'll first flash you the result, then I will take you through the theory, then we will come back to the result again. Okay. See here. So consider that you want to design a linear code of, it's basically a matrix. Okay. The code is now mapped to a constellation and it is transmitted. It has been shown that the pairwise error probability has, yeah, this is NR, this is a typo here. It is not N by R. Okay, this is NR and this is 1 plus lambda I. Gamma is a signal to noise ratio by 4 NT. NT is number of transmit antennas. What are lambda is? So you form basically a matrix FC minus FC bar, where FC and C bar are two different code words. Okay, this matrix, another independent matrix. Find the difference, multiply them. Okay, so difference matrix of two code words, conjugate of that together. Eigenvalues of these are lambda i's. If there are t non-zero eigenvalues, that means the rank of Fc minus Fc bar is t, then you have gamma power minus Tnr. That means your gamma decreases as a power of t power nr. So t is the transmit diversity term, nr is the receive diversity term, total diversity is given by Tnr. Your design criteria for space-time code: maximize the transmit diversity T first. Second, maximize the coding ng, that is basically geometric mean of the eigenvalues. Okay, these are the design criteria. Now I will tell you how these criteria have come. So till now I have introduced space-time block code, I have introduced example of space-time block code, and now I have told you what are the design criteria for space-time Brock code. Now I will prove the design criteria. Let us see how we calculate the probability of error in a CISO AWGN channel. Okay? Yeah, we are back here. Sorry for the brief interruption. So what you see is, in a BPSK you transmit two amplitudes, root E minus root E. I am seeing from the baseband. Now the probability of error is you transmit 1, receive as 0, or you transmit 0 and receive as 1. You transmit 0 and receive as 1. Using Bayes theorem, this can be rewritten as the following. Conditional of probability of deciding a 0 given 1 was transmitted, and conditional probability of deciding 1 when 0 was transmitting. Probability of 0 being transmitted, probability of 1. Now when they are equally likely, we can have, this is almost true, so we have PB0 equal to PB1 is equal to half. And because of symmetry of nature, probability of making mistake when 0 is transmitted is 1 is same as the problem that you decide 0, 1, 1 was transmitted. In this rule we have already defined y is greater than less than 0. This is basically your ML rule and you have derived it many times, so I am not going to do it again. Okay? And this entire simplification using the Bayes theorem, the equal probability message and symmetry, what you get is the probability of error is basically equivalent to taking either one of the case. So let us take the case that you decided 0 when 1 was transmitted, that is the error. So your CISO AWGN channel, so what you have received is y is basically what was transmitted minus epsilon or minus root of E plus the noise. What is the probability that y is greater than 0? So you just need to put in PDF and multiply. Yeah. So in PDF is Gaussian distributed. So I am simply substituting there, change of random variable, and you get the answer in the standard Q form. So you see that it is Q, the Marcus Q function which is defined as follows. Okay, root of 2e by n naught, where root 2e is basically the distance between square of distance between the two transmitted signals, right? This is for the AWGN case. This is basically just a review. Now, what I want is, what is the probability of error for the CISO AWGN channel over a fading channel? Okay. Now, for the CISO fading channel, now a CISO fading channel. Okay. So what you receive is y is equal to h x plus eta. Now what is the probability of error in this case? Entire derivation what we have done till before is valid under the case you have h given. So you have the probability of error given h as equal to q of root of 2 modulus of h square energy that was transmitted by n naught. Okay. So what is this itself, because of the h is a random variable, this itself, the probability of error is now a random variable. It is function of the channel. So what do you get? For ergodic channels, you have the average probability of error, that is PE, is basically equivalent to average of the conditional error probability over all possible realization of h. Okay. Now for this case we have assumed for the CISO channel h is complex Gaussian with 0 mean and variance 1. So in this case the PDF, this you can write it as P of E given h PDF of h square, whatever it is, say it is a function of x, d of x. It's just a repeat of the basics, okay? So nothing great about it. So the PDF of mod of h square is basically exponential. It's a simple function of one random variable, so it is exponent e power minus x, where the variable is x, comma x greater than 0. This is the PDF of h square. It's very simple, just substitute it and you will get that. So substituting in this equation and doing the maths, you will get the average probability of error of DPSK in a fading channel. Okay? Substituting and averaging. Do the maths. I'll give you the answer directly. It is going to be half 1 minus root of gamma by 2 plus gamma. This can be simplified as 1 by 4 gamma for large SNRs, okay, using the Taylor series expansion. So from here to here, this is your second exercise. Show that this is 1 by 4 gamma. There is another way, this is doing Taylor series. There is another way to go from there to here. That is basically use the upper bound on Q function. That is Q of x is less than or equal to e power minus x square by 2. Huh? This is called as a chain of 1. E of minus x square by 2. Okay? You can use this, substitute here, okay, and then derive, and you will get back, take the average over the distribution, you will get back this. Okay? In fact, you will get 4 into 1 plus gamma. You will get back this equation at high SNRs. Okay? So what follows, I will make a simplification, right? So instead of this, I am going to use the turn-off bound. Okay? Remember again, EB by N naught I have taken as gamma. Okay? So this can be written as exponential of minus gamma it becomes e power minus gamma, exponential minus gamma basically. This is bottom term, the 2 will cancel and this is what you will get. And then averaging this is what you will get again. Neglecting the 1 you will get after this. Okay? Do that, what do you get? Do it, so you will get, okay. So this factor is not so important. Maybe I have missed a 1 by 2 sign somewhere. That's okay. But the central point is this. At high SNR, this 1 is going to be small. So you again see that it is a function of 1 by gamma. So the probability of error is proportional to 1 by gamma. Previously we said it is an outage. Okay. Outage is proportional to now 1 by gamma. Now we are showing that the probability of error is also proportional to 1 by gamma. Okay. So that's why the previous statement that we made, that in a fading channel errors are due to outage, due to fading. It is not because of large AWGN noise. Okay. Now with this derivation I will slightly generalize it. Instead of CISO, I will have a CMO channel. Now I have a CMOS channel. So instead of y, now y becomes a vector. So you have y1, y2. You have single input, multiple output. Yeah. So this will become h1 or standard meso channel that we have started with discussion today. Okay? It's a CMOS channel, so only one axis transmitted. We are doing maximal ratio combining. So after weighing etc., you will have y tilde is basically h1. Let me write it as h bar. So h bar conjugate. This let me write it as y bar. Okay, is going to be equivalent to h1 square, h2 square, x plus theta. This is a seesaw equation now. Okay, this is only one equation. Now my question is find out the probability of error for this case. Given h1 and h2, what you see is there is a change in there is a change in SNR. So the probability of P given h1 comma h2, that is the probability of error of BPSK given h1 h2. Now you can write that as Q of root of SNR, whatever it is. Okay. So what is the SNR? Twice of. Okay. That is what is going to be a probability of error given h1 comma h2. Now average it over h1 and h2 using the Chernow bound, that q of x is less than or equal to half of e power minus x square by 2. Okay. Use this, average it out and tell me what is the probability of error of BPSK over CMOS fading channel. Yeah, just do the maths. Maths would be simple. So it will be 1 by 4 gamma power 2, because then h1 and h2 are independent, so there will be two separate integrations, and for the two separate, because of the additional term in the exponential, and that's you can actually write it as 1 by, it is proportional to 1 by gamma square. That is important. So two branches, that implies twice. So what you see is degrees of freedom is now reflecting as diversity order. Okay, so that is the second link I want to confirm. The degrees of freedom that the channel was giving was 2. Now it has been linked to the degrees of diversity order. It has been linked to the diversity order. In general, for example, you have L such term, or if you have NT-NR such term, it will become NT-NR. Okay, we are still not done. We are still at the CMOS channel. You can do similarly for QPSK, entire scenario. What you see is additionally this power factor of 2. Okay, and here it is in the terms of EV by N0. This is very exactly same derivation as what you have in ProACIS chapter 5. So just go and see that. The important point is this. What happens for more general channels? That's what I wanted. You have the union bound. What does the union bound say? That the more the complex the constellation becomes or M increases, it is difficult to find a closed form, so you need bound or approximation. One such bound and approximation is what is called as a union bound. Okay, so basically what it tells you is probability of union of certain events is equivalent to sum of probability of individual events. That's what this entire equation says. Okay. So now let us see that probability of error basically is summation of m equal to 1 to m, the constellation size, probability that xm was transmitted and an error was made into the probability of xm. Equally likely, so you get this derivation. Okay. Now, given xm, when do you make an error? When the received signal distance is nearer to any other symbol xl that is different from m. Okay. So summation all such events is basically your probability of error given xm. Using union bound, it is simplified here, and then again we have used this probability that for a given L, this happens when you transmit XM and decode it as XL. So that is what is called as a pairwise error probability, probability of choosing XL instead of originally transmitted XM. Given XM was transmitted. Okay, so this interior thing. This is again union bound is a worked out example in your chapter 5 in digital communications case. I am just revising that, and I lift it for our case. Okay, now further simplifications etc. and using proper notations, you see basically it is this you can put it as Q of D of LM to sigma. Okay, where DLM is the distance between the two symbols XL and XM. Okay, using the Chernoff bound, this is what you get, DLM by 4 and not. But calculating so many DLMs are different. So you make one more simplification. It says because if you take minimum of all possible distance, rest of distance will be larger. So they will have a smaller term. So this will be an upper bound if you take d mean and simplify it. So this is the final derivation in, and then you substitute in the probability of error and you get this term from the union bound perspective, and that is what I am looking at. More importantly, that is the pairwise error probability. Okay. In the multi-dimensional error case, you see the number of possibilities is not m, it is going to be m power nt. Okay. So, but what dominates is the pairwise error probability of the minimum distance. So, for a MIMO space fading channel with space time coding. So, without space time coding, you would have Y is your received signal, H is the NT, NR cross NT transmit matrix, X is your NT cross 1 transmit symbol, eta is NR cross 1 noise added by the receiver. You add index time duration x1, x1, xi, eta, okay, collect them as columns here. So you have y1, y2, you are doing it for L time durations, yl is equal to, H will remain as it is. You will have a matrix here, x1, x2, xn, okay, plus eta 1, eta 2, eta n, because you are using over L time duration. So now you have your space-time equivalent channel matrix for MIMO as following. Okay, where theta is, remember, NR cross L matrix. Your X is NT times L matrix and Y is NR cross L matrix. Okay, the entire notation has changed. What is the pairwise error probability in this case? That there were two different codes, X1, X2 were transmitted. Suppose there are two codes, PX1 and what is the probability of deciding as X2 given X1 was transmitted. Okay. So I have just lifted the notation from or the idea from the union bound for probability of error derived for general constellations in your book for the space-time course. Okay. Using that, what would that be? We already know it is going to be exponential minus distance between the two symbols x1, x2 by 4 or 2 and not. Whatever it is, the factor of 4 or 2 and not. It would be 2 and not. Huh? No. D12 is the distance between that. What is the distance as seen from the receiver? D12 would be equal to Frobenius norm of H x1 minus H x2. This is going to be your distance. Okay? Remember that I had already developed the concept of the transmit vector being changed to a different dimension by the channel matrix H to the receive vector dimension. So Hx1 is the received projection of x1 in the received signal space. Okay, and the distance between those two is what matters. This is of course given the channel matrix H. Right? So first we have stacked the MIMO channel model to get the space-time channel model equivalent. Then we have used the pairwise concept developed for union probability of error and we have applied it here. Okay? And third difference from the AWN case, we are finding the distance as seen from the receiver side, not from the transmitter side. Okay? That is distance. This can be simplified. Okay, so x1 and x2 are the difference matrix. It is the distance between these two that matters. Let me further simplify this. D12 square would be written as trace. This is just a matrix notation. I'm using properties of matrices basically. So you have H of x1 minus x2, x2 minus x1 or x1 minus x2 conjugate H conjugate. Okay. Now diagonalize this. Use the similar value representation. This is a NT cross NT matrix. This inner matrix in the braces, it's an NT cross NT matrix, right? Eigenvalues of this, you can write it as U lambda U Hermitian. Okay, H. This, a unity matrix multiplying a Gaussian matrix would again be Gaussian distributed. So this becomes H equivalent, this becomes H equivalent, and this becomes H equivalent star. Okay, so this is basically trace H equivalent lambda h equal. You just do the maths there, you will get NT-NR terms, and those will be non-zero if and only if eigenvalues of lambda are non-zero. Yeah, because of shortage of time I have to speeden up. So by substituting that and then averaging with respect to h, okay, this is how you will get this equation. If p of the eigenvalues are non-zero, this is what you will get. Okay, so that basically gives you how to design the space-time block codes, okay, by trading off complexity of decoding. Outage concept, I will still, it requires a little more, but what we have designed is an average error reducing code. We have not designed an outage achieving code. Okay? But we started by saying that we want to derive an outage achieving code. Okay, that is a little bit more involved. Maybe in the module 2 I will address it. There is another possibility. What you have is this entire theory that we have developed for space-time codes, maximizing the diversity rank between difference between two transmitted code words, okay, and the geometric mean can be applied to space-time frequency code, but by replacing the time index with the tone index, okay. So for example, you can have, but the important point is by replacing this index, what you would require is the channel be constant over two, instead of symbol periods, 2 channels. It is not just enough that adjacent channels is sufficient. You can take anywhere 2 channels that are even apart, but they are equal. So this is the problem in frequency selective channels, okay, and such codes are called as frequencies, space frequency codes. This entire theory can just be lifted exactly from there. I have given one example in your exercises, okay, quiz 5. In the assignment, I think assignment it is problem 2 that I have given what is called as the golden code, and I have asked you to do analysis for the golden code. Please do that. To summarize that, we have now introduced that, shown that the main problem of space-time coding is decoding. It makes decoding complex. OSTVT solve that, but the problem is still very complex. Okay, because it pays penalty in terms of rate. So general space-time codes can be designed by using various approaches. People have designed codes that have a little higher complexity called quasi space-time codes that achieve a better rate, but a general theory of trade-off of decoding versus the diversity order is still missing. Okay, so that is an open area. Hope that excites you to do some work there. Then this entire theory can be lifted to space frequency codes. That is the summary for today's lecture. There is another use of MIMO that is given in example here. What you see is, let's call interference cancellation. So what you want to do is, you want this guy, in a general case, he would transmit in such a way that in addition to the, see, LIC is the blue one, both the transmitter, receiver and Bob is the green case. So what Bob is transmitting will interfere with LIC. But what you can do is choose H1 alpha is equal to minus H2 beta such that what you received at the receiver of A is 0 and it is not 0 at what you received at the second case. So this is the concept of interference cancellation and alignment. So this is the third use of MIMO. So MIMO you can use to increase capacity, to increase reliability by getting diversity. You can use it to cancel interference from unrequired places. Okay, so these are the use cases of MIMO. So MIMO is a powerful tool. It gives 4 different possible applications, and space-time codes is basically a way of achieving first 3 of them. Okay, space-time codes for interference cancellation, I am not looking at that, so I will not make a comment there. So that is the summary of the course till now. Present case, most of the standards are looking at MIMO, but they are looking more at massive MIMO. Okay, when you have large number of transmit receive antennas, the problems there are entirely different, and that would be the topic of discussion for the second module that will be happen in the next semester. Okay, so with that I am stopping the lecture now. And opening the floor for various discussions. So references, lecture notes, etc. This is essentially chapter 8, 7 and 8 from David Sayers book. Some of the review papers here, okay, and the tutorials given in this. So these are the reference material. I would request you to do the total 10 problems, 5 given in the assignment here, 2 assignment problems today, 3 last lecture. So total 10 assignment problems I would request you to submit, and based on the performance there I will decide how we will take the next module or the continuation of this lecture. Okay, questions please. I hope you at least got the intuition of how things are working. For the MISO case, you prioritize, I have given you only one example, that is maximal ratio combined. So when you multiply by H1 for the first user, H2 for the what you received as a, for a MISO channel, how can you prioritize it?
When more transmitter signals, it's being received by a single receiver. How do you just prioritize the signals in case of more number of transmitted signals occurring at a single receiver to receive them?
See, the for first case, if you are using L-multi code, okay, so there is no question of prioritizing because both of them are being decoded independently. For the case when the channel is known as the transmitter, for that case you can prioritize it. Maybe you give more weightage to other by based on its channel characteristics. Maybe you reduce the transmit power on one channel and increase it on other channel. That you can do. But without the channel information available at the transmitter, you cannot prioritize it. Does that
Okay,
answer your question?
Yes, sir.
Case RCT. Your question is, can we practically achieve high data rate for MIMO system than single output? Yes. So the multiplexing gain is basically achieving high data rate as compared to CISO output. See, if you would see the definition of linear space-time codes that I defined, block codes, I is equal to 1 to L. The moment your L is greater than your number of symbols Xi is greater than number of channels or the number of channel uses or the dimensions of the A and B matrices, right? Then so when capital L is greater than, so you just see the notes where I have defined linear space-time block codes. Okay, capital L is number of symbols. Okay, dimension of the matrix A and B, that give you the number of time uses that you are that are channel uses that you are using. Okay, so the ratio of that will give you the increase in data rate. Okay, if that is greater than 1, you are getting more data rate. If it is less than 1, you are getting less data rate. Okay. Okay, then there are no other questions. I request you to do some of the maths. Again, this is a course in applied maths. The name is MIMO, but the way I have taken this course is I have introduced concept, then introduce terminology, then develop the concepts by deriving the maths. I didn't derive the full maths completely, but I have given you hints and intuitions that would link to what you already know from digital communications. So I hope that would be comfortable, and I will request you to fill up the blanks by completing the gaps that I have done. If I get questions, or if you are still have doubts, questions later on while you are working out, I request you to please send an email to me. I will be more than happy to answer those. Okay, so happy vacation then, or happy holiday period then. Thank you.